In the late 1970s, Ellie Godrak created and later codified the drum buffer rope scheduling approach for manufacturing. About 30 years later, Ellie Schragenheim, one of Godrak's longtime collaborators and friends, simplified DBR and created Simplified Drum Buffer Rope, or SDBR for short. SDBR assumes four conditions and in doing so greatly reduces the complexity of implementing the drum buffer rope approach. This means it is easier to implement and gets results quickly. The first assumption that we will explore is that SDBR assumes that the market is the constraint of the organization. You'll probably recognize this diagram from previous videos, and it's worth pointing out now that it is firstly based on a real plant that I worked in and successfully implemented SDBR in, and secondly that I've created a simulation based on this plant that uses dice and counters and allows us to explore the process of implementing SDBR. If you'd like to know more about the simulation, how it can be used to educate your people in SDBR, and how it improves performance, watch part 3 of the On Time in Half the Time series where all is explained. We're going to use this diagram throughout the video to explore what happens when we implement SDBR and transition from a high inventory plant to a low inventory, high velocity plant. So let's quickly recap before we return to the discussion. Each of the coloured bars represents a work centre, and work in process flows through the plant from left to right. The numbers in the bars represent the maximum capacity of that work centre per day, and as you can see, the capacities vary from 12 to 18 units per day. The constraint in this organisation is market demand. If you look to the left of the process flow, you can clearly see that market demand is for 6 units per day, and this is less work than the plant could actually cope with. Now I've made the plant even more lifelike. The grey bars represent the amount of inventory or WIP that is queued in front of each work centre. The number in the bar tells you how many units that are waiting. The queues are quite big, with most being 30 units, and the queue in front of one work centre 6, being 60 units. This begs a question. How on earth does it get to be so much inventory in the plant when market demand is the constraint? All of this can be quite confusing from an internal perspective. With so much inventory in the plant and so much delay, it would appear as if the constraint were actually in the plant. You could be forgiven for thinking this, but we have to remember why the excess inventory is in the plant in the first place. It is there because we put it there, not because we're being swamped with demand and don't have the capacity to cope. For this plant, the market remains the constraint, and it is the constraint that determines the output of this system. The next simplifying assumption that SDBR makes is that there may be a capacity-constrained resource in the plant. This is significantly different from the traditional drum buffer rope approach, which assumes that there is either a bottleneck or a CCR in the plant, and that it will require careful scheduling. The third simplifying assumption made by SDBR is that the touch time of a unit going through the plant is less than 10% of the total elapsed time. You'll remember from the efficient and unproductive videos that I asked you which journey to work would take you longer, the journey that starts at 3 am or the journey that starts at 8 am. You're the driver in both journeys, the route and the car are both the same, so which journey takes longer? Everybody answers this question by saying that the journey that starts at 8 am takes significantly longer, and it takes longer because of the extra traffic on the road. The extra traffic creates queues, and it is the time spent in the queues that accounts for the difference between the two journeys. It is the same in the manufacturing plant. When our plant is full of inventory, there are queues in front of almost every work centre. The queues dramatically increase the time it takes for a work order to go through the plant, and the additional time is accounted for by the time the work order spends in the queues. Another interesting way to think about this is to ask yourself how many units are there in an average batch in your plant. If the answer is 10 or more, and the units are processed 1 unit at a time, then the ratio is at least 1 to 9 of touch time to elapsed time. For many environments, the number of units in a batch is at least in the tens, and many are in the hundreds, and some are even in the thousands, and therefore the ratio is much higher. For example, I once worked for a client who had 5 weeks of inventory in front of the CCR in their plant and several weeks worth of inventory moving through the plant either side of the CCR. The average batch size was around 2,000 units per work order, and the actual touch time, the time taken to actually process the unit from raw material to finished product ready for shipping, was under an hour for almost all products. touch time was much less than 1% of the elapsed time in this plant. This wasn't an outlier either. I've encountered many plants where the ratio of touch to elapsed time is at least 1 to 99, or in other words, over 99% of the time the work order was in the plant, it was sat in a queue doing nothing of any use. You'll be relieved to hear that after we implemented SDBR, we got the lead time down from over 50 days to just 8 days with over 99% due date performance. So, provided the ratio of 1 to 9 holds true for a given plant, SDBR is likely to yield good results. The ratio in our little plant is difficult to determine because of the way the simulation is designed. More about that in part 3. But it will serve us just fine for the purposes of illustrating the impact of SDBR on the plant's performance. I've run the simulation on numerous occasions, and I cannot remember a single occasion where a work order introduced to the plant with the same starting conditions as these on the diagram has taken less than 28 days or more than 32 days to complete its journey through the plant. As I mentioned, if you want to know more about the simulation, watch part 3 of On Time in Half the Time, but the important point for us in this discussion is that the elapsed time is far greater than the processing time. The fourth simplifying assumption made for SDBR is that we only use one buffer and it's called a shipping buffer. Now, to properly understand that statement, we need first to understand a little about the original drum buffer rope method developed by Ellie Goldratt in the late 1970s. Goldratt's original DBR method had 4 main elements to it: the drum, the buffer, the rope, and buffer management. I'll describe the first 3 here as they are directly relevant to what we are discussing. Firstly, DBR nominated one resource, usually a bottleneck or at least a CCR, as the drum. The drum acted as a focusing and synchronizing point for the whole plant. To follow the analogy, the drum beat the pace at which the whole plant marched. Being either a bottleneck or a CCR, DBR placed great emphasis on finite scheduling of the drum's scarce and precious capacity. This was done to protect the throughput of the organization, which was determined by the output of the drum. It was the constraint. The second element of DBR was the buffer. The buffer also served to protect the drum's capacity. Except in DBR's case, the buffer wasn't a physical pile of inventory waiting to be processed, but a generous time period which allowed inventory to get from raw material release to the drum and be available for its slot in the drum's schedule. The third element, the rope, protected the plant from being flooded with too much inventory, the downsides of which we are now familiar with. The rope prevented inventory from being released into the plant more than a buffer time ahead of it being needed by the drum. So, for example, if the buffer was 7 hours and the work order was scheduled to be processed by the drum at 1600 hours, the raw material would be released at 900 hours, thus giving the work order 7 hours to make its way through the various work centres preceding the drum and be ready for processing at the drum ahead of its scheduled time on the drum. Now, when you're scheduling a plant with hundreds, perhaps even thousands of work orders being processed simultaneously, you can imagine the calculations are numerous and starting to get very complex. Especially when you consider Murphy's Law, i.e. anything that can go wrong will go wrong at the worst possible time, applies to manufacturing plants. In addition to this, DBR had a number of different buffers that could be used to protect throughput. I'll explain each of the buffers with some help from a diagram. This slide depicts a routing for 2 products through a plant. You'll notice the flow sits on a grid with numbers going up on the y-axis and letters going across on the x-axis. This enables me to give you a grid reference, and you'll know that when I say E4, it relates to the light green circle with the number 4 in it. Everyone got that? Good. Flow starts at the bottom of the routing at material release. You can see the circles with MR in them, and flows up the routing to shipping at the top. Each circle represents an operation in the routing. The colour represents the machine the operation is performed on, and the time in the circle tells you how long the operation takes to process each unit. So, for example, E4 is an operation on the light green machine that takes 4 minutes per unit. We have 2 products in this example, one shipping from C8, which we'll call product C, and one from G7, which we'll call product G. So what does implementing DBR look like in this little plant? Well, the first thing to note is that we have nominated a drum resource, and it is the blue machine. And as with any drum, we need to schedule and buffer it to protect throughput. However, As we're talking about how buffers work in DBR, you'll be relieved to hear that I'm going to skip the scheduling bit. In Goldrat's original DBR method, a buffer is used to protect throughput at the drum because its capacity is so scarce. I've seen it called a drum buffer, the internal constraint buffer, the CCR buffer, and a few other things, so feel free to pick your favourite so long as you remember that the point of the buffer was to protect the drum resource from starvation. The buffer is a period of time that the plant allows inventory to flow from raw material release to the drum and be at the drum in good time for its scheduled time for processing by the drum. As I mentioned above, the buffer wasn't a physical pile of inventory, it was a period of time. If the buffer was long enough, it would certainly result in a pile of inventory in front of the drum, but in DBR the buffer incorporated all of the inventory waiting to be processed by the drum and the inventory flowing towards the drum. This is a subtle but important difference to other manufacturing scheduling techniques. If you look at the diagram, you can see the chalky red lines that depict the drum buffers, the buffers that protect the drum resource operations. The looping style of the line is intended to convey that this is a liberal estimate of the time needed to get from raw material release to the drum. In this little plant alone, there are 4 drum buffers from which you can calculate, when you know the drum schedule, the exact release times for raw material. It's also possible in DBR to give each of the drum buffers their own time period. The advantage of this being that you prevent inventory from going into the plant too soon for drum operations that are close to raw material release. On the other hand, you may wish to use a longer buffer to ensure inventory has enough time to get to drum operations that are far away from raw material release in the routing. As you can see though, this is starting to get complex, and that's why early adopters of the DBR method bought the scheduling software that Ellie Goldrat developed to perform the necessary calculations. But we're not done yet. There are more buffers than just drum buffers. Next up was shipping buffers, which you can see on the diagram as chalky green lines. Traditionally, shipping buffers were used to protect throughput after the drum and ensure that work orders got to shipping on time, hence the name. Shipping buffers protected throughput from stoppages to resources that processed inventory after it had been processed by the drum. This meant that DBR plants had exceptionally high due date performance. The other way in which shipping buffers could be used was for products that didn't require any capacity on the drum due to their routing not including operations performed by the drum. These products were called free product, and a shipping buffer was used to ensure the free product was shipped on time. In this case, the shipping buffer was a liberal estimate of the time the plant allowed for free product to get from raw material release to shipping. This is a slightly arcane point, so I haven't included an example of this in the diagram, but just imagine a shipping buffer running from raw material release all the way to shipping for a routing that does not include the blue machine. Next were assembly buffers. There is one assembly buffer on this little routing which you can see in yellow. Assembly processes are notoriously difficult to manage due to the complexities inherent in ensuring all of the required parts to assemble the final product are in the right place in the right quantity at the right time. I remember visiting a plant that made designer glasses some years ago, and it was a great example of this. We walked through the plant, beginning at operations close to material release, and I noticed that there was very little inventory, just a few piles of containers at each work centre. When I got to assembly, I had to stifle a laugh because here the containers were stacked literally to the ceiling. When I asked why, the predictable response came back. They were waiting for the right parts to catch up. They had the right side arms of the glasses and the fronts, but not the left side arms. For other designs, they had the left side arms and the fronts, but not the right side arms, and so on and on and on. Entirely predictable in a conventionally managed assembly operation. When a drum resource feeds an assembly, throughput is delayed if a part feeding the assembly from a flow or routing that doesn't use the drum resource is not available as it should be or in sufficient quantities. In a plant using DBR, an assembly buffer was used to give parts enough time to flow from raw material release or a drum to the assembly process and be there in good time to meet up with parts that have flowed from the drum resource. This prevented parts that had used scarce drum capacity from being needlessly delayed and converting them from inventory into throughput as quickly as possible. Finally, in certain line configurations, space buffers could be used to deliberately unbalance the capacity. Lines are characterized by automated flow between resources, car assembly being a classic example. However, Lines can be very unreliable as a stoppage anywhere on the line meant the drum resource stopped and throughput was lost. A stoppage upstream could stop or starve a drum of inventory to work on. A stoppage downstream from the drum would also stop the drum due to inventory being physically unable to flow away from the drum. In this case, a space buffer was used to decouple the drum from the upstream and or downstream resources. This buffer allowed inventory flowing to the drum to congregate at the drum and provide some protection from stoppages upstream. Or, if the space buffer was downstream from the drum, it allowed the drum to continue processing inventory during a stoppage to a resource further down the line. This protected throughput as the drum did not stop. There was somewhere for the inventory to go while the stop resource fixed the problem and got working again. As the downstream resources had protective capacity relative to the drum, they could catch up after the stoppage and process the output from the drum. Now, I'm sure you'll all agree that this is getting really quite complicated, and you don't have to have much scheduling experience to imagine the knock on ramifications to the drum schedule and the material release and shipping schedules of a customer requesting a change of quantity or shipping date, a breakdown, or any of the numerous other things that can happen in a plant and change the best laid plans of the scheduling department. In fact, without software to assist, it was extremely difficult, if not impossible. So when Eli Schragenheim invented SDBR, he made the genius decision to do away with most of this and simply use shipping buffers. This makes perfect sense. If you are assuming that the market is the constraint, it is inevitably the case that all resources in the plant have protective capacity relative to market demand. This means they can catch up after a problem. The effect of capacity being left idle for periods of time or used to produce work orders out of sequence has far less impact than it would be the case if the plant had an internal constraint, specifically a bottleneck in production. And what if there was a bottleneck or CCR? Well, in fact, the chances are slim. Personally, I've only ever seen one real bottleneck, and that was debatable. Machine capacity is so cheap these days and manufacturing lead times so competitive that plants with real bottlenecks are few and far between. In fact, unless they have a product where scarcity is part of the cachet or offer, like a new model Ferrari for instance, they either go out of business or they typically get rid of the bottleneck by buying more capacity. Which, of course, is the most sensible thing to do. Why live with a bottleneck? It makes no sense for most organizations, and it almost certainly guarantees you will not grow your sales. But rather than spend your way out of trouble, why not first try all of the ways to increase capacity at the CCR that had been developed and perfected by the pioneers of drum buffer rope over 3 decades of experience? We'll explore all of the different ways you can do this later on. But for now, all we need to be clear on is that without a real bottleneck, which is a reasonable assumption, there is no need for detailed finite capacity scheduling. And if we don't need finite capacity scheduling at the drum, we don't need the drum shipping and assembly buffers typically used in a DBR implementation, not to mention space buffers. And if that is the case, we can make another reasonable assumption that just one type of buffer, the shipping buffer, will be sufficient to do the job. This greatly simplifies implementation of the SDBR approach and its ongoing operation. Moreover, it is sufficient to get us to a very high level of plant performance and very quickly too, as we shall see.